Um, uh, Welcome to my YouTube channel. Yeah, Samuel Nkwangu, as you can see below. Actually, today we are going to see how we can prove that an estimator, it could be alpha hat is blue. Alpha hat as in an estimator being blue. We want to see how we can prove this estimator as in being blue. If someone talks about being blue, blue means that like this estimator is the best. Like as in B means the best. B is the best. L is linear. Then U is unbiased. Then E, it is like as in an estimator, best linear unbiased estimator. That's what they are trying to mean. So we have seen in previous video whereby I show you how we can prove that beta hat is blue. So we saw that one already, but today we want to see how we can prove like this estimator as in being blue. So first of all, we have to show that this estimator is linear, as in we know that from our regression line, like the equation, our dependent variable y equaling to alpha is the intercept, beta xi plus the error term. So it all comes from this way. We say that we want to test and see test for linear. We want to test for linear. Remember, since we as well know that it should be linear, so we have to first of all you have to facilitate your alpha hat to be the summation of ki yi. So this is an indication of linearity, whereby this estimator, the alpha hat, is a linear function since it has an independent variable y. So let's define our ki, where let's say where ki is the same as 1 over n minus small xi over summation of small xi squared x bar. That is our ki. But we know that our small xi is the same as capital Xi minus capital X bar, and our small yi is the same as capital Yi minus y bar. So this will imply that our alpha hat will equal to the summation. Now we are substituting this into this. Let's assume this is equation 1. So we are substituting this ki into equation 1. So it will equal to will be 1 over n minus xi over the summation of xi squared x bar yi. So alpha at will equal to summation of yi over n. Remember, once this comes now, like once you open these brackets, you will remain with yi over n minus again the summation of probably it could be xi x bar yi over the summation of xi squared. Again, we continue. This is the same as summation of yi over n minus x bar. I'm very sorry, I'm going to skip some steps since I'm just being affected by time. Yi minus y bar over the sum of SSE of x, summation of xi minus x bar squared. But we know that the whole of this, we know that the whole of this is beta hat. Hope we all know that. Yes, whenever we are estimating it, the whole of this gives us a beta hat. So it will imply that this will imply that my alpha hat will equal to y bar minus beta hat x bar. So that's what we've got. You can as well conclude and say hence alpha hat is a linear ordinary least square estimator of alpha. You can conclude. Now we are done with that, checking whether it is linear. So let's go to unbiasedness. Now we are going to check whether alpha hat as our estimator is unbiased, checking for unbiasedness. So let's check and see whether it is unbiased. So we say from previously, you know that alpha hat, we defined it as it is the same as summation of kiyi, but we are going to take expectations both sides. Let's take expectations both sides. So probably expectation of alpha hat will equal to the expectation of the summation kiyi. Yeah. So expectation of alpha hat, once we take the expectation, really sorry, we are going to skip some space. Now we are going to substitute for yi. Remember our yi is here. That is our yi. So we are going to substitute to say that it is the same as summation of ki into alpha plus beta xi plus the error term. So this is the same as expectation of let's say this is summation of alpha ki plus beta xi beta xi ki plus ki, the error term I. So again, remember this is the same as again expectation of now we are going to enter this summation. So alpha summation of ki plus beta summation of kixi plus summation of ki error term I. So this one in that. So by considering the when you impose, let's say by imposing unbiasedness as conditions or assumptions, probably could be conditions. So we know that the summation of ki will always give us 1, and the summation of kixi will equal to 0. So the expectation of the sum of kixi, the sum of ki error term I will also give us 0. What does that indicate? That we are only interested. Remember, we want to see whether this alpha hat is unbiased, and we would like to drop off this the second term and the third term also. We'd like to drop them. That's why you come up with those conditions to make our work easier. But probably they are the conditions for the unbiasedness. So let's continue. On substitution, you'll get expectation of alpha hat will equal to expectation of alpha times 1, so which is equal to expectation of alpha. So we remain, remember alpha is a constant, remaining with a constant, so expectation of alpha hat, it will give us that constant. So then we again conclude by saying that hence alpha hat is unbiased ordinary list, is unbiased ordinary list square, is unbiased ordinary list square estimator of alpha. So now we are again going to continue and check whether this estimator is the best. Remember from blue, you are going to check and see whether it is the best estimator. Why best? As an estimator, it will be best if it is more efficient. Being efficient, it then means that it should have the least variance amongst all other estimators. So we are going to check, checking whether alpha hat is the best or more efficient estimator, is the best or more efficient estimator. So we know that from variance, let's say variance of alpha hat is the same as taking the expectation of alpha hat minus the expectation of alpha hat itself, the whole of that squared. But we know that our alpha hat is the same as the summation of ki yi. Also, the expectation of alpha hat, we saw it already that it gives us the alpha. So our variance of alpha hat is equal to the expectation. Now we are substituting expectation of the summation of ki yi minus the alpha, the whole of that squared. So let's continue on continuation. Where is that one taking us? Variance of alpha hat is equal to the expectation. Now we are substituting the summation of, yes, I'm going to skip a step whereby I'm going to introduce the yi here. We know it already. I'm going to introduce the yi here. So I'm going to skip a step whereby it is the same as the summation of alpha ki plus beta summation of ki xi plus summation of ki, the other term I, summation of ki other term I minus the alpha, the whole of this squared, the whole of that squared. So yeah, the whole of that squared. So then on continuation, let's continue. Previously we say that for unbiasedness conditions, we know that the sum of ki xi is equal to 0, and the summation